Assalamualaikum warahmatullahi wabarakatuh. We are in the lecture 7, week 7 of our lecture. Okay, so let's proceed to the slide. Okay, previously we have learned that accumulation is equal to output minus input and generation minus consumption, and that if there is no accumulation, that means input minus output equals generation minus consumption, or in other words, this process we call it as a steady state process. And also in the previous class, I have also explained about number of degree of freedom. We can label it as NDF, okay, where number of degree of freedom is equal to n unknowns minus n independent equation. Okay, so there are three possibilities where the first one is number of degree of freedom equals 0. There are n independent equation in n unknown, and the problem can be principle be solved. Second one is number of degree of freedom is greater than 0. There are more unknown than independent equation relating them. And then finally we have a number of degree of freedom is less than 0. There are more independent equation than unknown. So for this one we cannot solve because we have um, more unknown than the independent equation. Okay, now let's look at the example. If we have a stream of humid air enters a condenser in which 95% of the water vapor in the air is condensed, the flow rate of the condensed is measured and found to be 2 to 5 liter per hour. Okay. Dry air may be taken to contain 21 more percent oxygen. Okay. With the balanced nitrogen. Okay. Balanced nitrogen means we have 79% mole percent of N2 here. Calculate the flow rate of the gas stream leaving the condenser and the mole fraction of oxygen, nitrogen, and water in the stream. So we need to find several parameters here, right? No, now if we are going to draw a flow chart, so we have been told that humid air enters a condenser, means this is our condenser. Okay, condenser, and then we have where we if we have the term humid air, means we have dry air mixed with water, right? So means this whole stream is humid air, but we have dry air mixed with water, and then which 95% of the water vapor in the air is condensed, means here we have one product, 95% of water in feed, so we can label as N3, and that means flow rate. So we have mole H2O liquid per hour because this is condensate, and then we have N1 as mole dry air per hour because we don't know what is the flow rate of mole dry air, and then we have mole of H2O, also we don't know, that's why we label as N2. So far we have three unknown already, and then the flow rate of the condensate is measured and found to be 2 to 5 liter per hour. So here it is given in liter per hour, but the unit is in mole per hour for N3. That means we already have information here, but we need to convert the unit later on to mole per hour from liter per hour. From this question, we have been asked to calculate the mole fraction of oxygen, nitrogen, as well as water. So we have another three unknown, where N4 is for O2, N5 N4 for oxygen, N5 for nitrogen, and N6 for water. Now for this question we have 1, 2, 1, 2, 3, 4, 5, 6 unknown. So from previous slide we know that we have 6 unknown, right? That means we need to have 6 independent equation. So what we have previously is we have 3 material balance. Let's look at the flow chart again. Okay, so we have mass balance for this part. Okay, um, where we have the first, we have total mass balance, where we have n1 plus n2 equals n3 plus n4 plus n5 plus n6. Okay, this is easy because we know that we have two inlet and then we have two outlets, where the first outlet we have n3, the second outlet we have n4, n5 and n6. So this will be our total mass balance. So this is the first independent equation that we have, total mass balance. And then we have component balance, where we have balance for H2O, right? So if we do for H2O, okay, we have N2 equals, okay, H2 is here, here, and here. So we have N2 equals N6 plus N3. Then we can finally do mass balance for dry air, for air, where we have N1 equals N4 plus N5. Why? Because here we have dry air, we have O2 and N2. So that means N1 is represented by O2 and N2. And then here we have O2 and N2. That's why we have N1 plus equals N4 plus N5. So based on this, we know that we have three independent equation, where this is number one, number 2, and number 3. And we have 6 unknown. That means we cannot solve this equation yet. Since we only have 3 independent equations, that means we need to find more additional relations to solve for another 3 unknown. So the first one, we have relationship between the volumetric and molar flow rates of the condensate to determine N3, because we have been given with the flow rate of H2O in liter per hour. And then we have information of 95% water condensate. It provides a relationship between N3 and N2, where N3 equals 0.95 N2. So we can add another 2 independent equation, but no information provide a basis for establishing six relations, so that there is 1 degree of freedom. That means we don't have enough information to solve this question. Provided we have been given with a new information, where entering air contain 10 mole percent of water. So instead of we have 6 unknown just now, so we only left with 1, 2, 3, 4, and 5 unknown. So we have 5 unknowns. Okay, because previously N2 we have here for this, right? So we can omit that part because we have been given with this new information. Okay, so that means we are left with 5 unknown only. So previously we also have 5 independent equation. That means we can solve this equation after we have been given with this information. Now let's solve this question. The first one is N2. We have been given in terms of liter per hour, so we just convert the unit by using, yes, by using density. We have this, right? Density equals N over V. So we can find number of mole. Then we also have N equals M over MR. So we can use these two equations to solve to convert the unit of 2 to 5 liter H2O per hour to mole H2O per hour. What we need to do is we just times with the density, okay, and then divide with the MR. Sorry, we divide with yeah, the MR. We do get this relationship, right? So since we have these two equation, what we can do is we don't want mass, right? So we can express this in terms of mass. So M equals rho V, first equation, and we have M equals N times MR, second equation for this one, right? So we can make it like this: 1 equals 2, okay, 1 equals 2, which will give us rho V equals N mR, and then we want in terms of mole H2O per hour, right? So what we need to do is we express N in terms of rho V over mR. So we can rearrange the formula. We have N equals rho V over mR. Okay, that's why here is our V. Okay, this is our V, this is our rho, this is our mR. That's why we can use this formula to solve to convert the unit of liter H2O per hour to mole H2O per hour. We have second information where we have been told that there is 95% condensation. Okay, if we go back to the question, okay, here we have 0.1 of H2 times with N1, because this is the total the sorry total molar flow rate for this stream. That's why for H2O we need to take 0.1 times with N1. That's why then we will get the flow rate of H2O, and then we know that N2 is the output. In other words, 95% from the inlet will give N2. That's why we have N2 equals 0.95 from the inlet stream of H2O, which is 0.1 times N1. So we have this second independent equation. Next, our third independent equation is we can do O2 balance. Okay, if you go back to the slide, we know that we have total molar flow rate for inlet, and then we have 0.9 mole dry air. So we know that dry air is 0.9 times with N1, and then for N2 we need to times with 0.79. For O2 we need to times with 0.21, and then the outlet for O2 is N3, the outlet for N2 is N4, but we need to do it independently. That means if we do for O2 balance means N1 times 0.9 times 0.1 equals N3. And for N2 balance, N1 times 0.9 times 0.79 equals N4. Where N1 times 0.9 is the dry air flow rate in the inlet stream. Okay, but for O2 we need to times 0.1, N2 we need to times with 0.79, and then N3 and N4 is the molar flow rate for outlet stream here. Okay, last but not least, we do H2O balance, where we know that this is the molar flow rate for H2O for inlet. Okay, let's go back to the diagram. N1 times is 0.1. Okay, and then we have N2 plus N5, because here is N2 for H2O, and then N5 is for H2O as well. So that means for this one we do mass balance for H2O. So what we have is 5 equations or independent equation with 5 unknown. So you can solve it via algebra. So we'll get this answer. Try to do it. Okay. So for total outlet gas flow rate is N2 plus N3 plus N4 plus N5, because we have this part N2, N3, N4, N5. And then for outlet gas composition, what we need to do is we need to find the N total, add all of this, and then we can find composition for O2 by taking this N3 over N total, and then the same goes to N2 as well as for H2O. Why we need to find this composition? If you go back to the question, we need to calculate the flow rate of the gas stream leaving the condenser, in which we already find N1, N2, N1 till N5, and then the mole fraction of oxygen, nitrogen, and water. So mole fraction of oxygen, nitrogen, and water in this outlet stream. That's why we need to do that. I need to do this calculation. Okay, that's all for the first part of this lecture slide. So next we will learn about stoichiometric ratio in the next part. Thank you.